Hi, everybody. Welcome to today's edition of the Spectral Geometry in the Cloud seminar. Before we start, I want to say we've had with the CRM some problems with some Zoom bumping in the last few weeks. So there is a backup Zoom link that's ready, and if it happens, I will close this this Zoom instance and send a new link within a minute or two to the mailing list. Let's hope we don't have to do that, but in case it happens, this will be the procedure. In better news than talking about Zoom bumping, today we have as our speaker Francesco Ferraresso, who will talk to us about Neumann and intermediate biharmonic eigenvalue problems on singularly perturbed domains. So Francesco, the floor is yours. Thank you for speaking here.
Thank you very much, Jan, for the introduction and for the kind invitation to this extremely interesting cycle of seminars. So this talk, I'm mainly interested in domain perturbation theory for the biharmonic operator. And I will mainly consider either Neumann or intermediate boundary conditions. So let me get started with an outline of what I want to do, if I can actually make this work. Okay. So I will start with an introduction about the main results that are known, and I will focus on the Neumann Laplace operator, and I will show what is known, at least in that case. And then I will try to make a comparison with the biharmonic operator. And we will see that there are several interesting differences. Once we have done that, I will consider the biharmonic operator with intermediate boundary conditions first. And then I will switch to the Neumann biharmonic operator, first on Dumbbell domains and then on thin annuli. So the general framework of this talk is the one of domain perturbation theory. And the main problem you should have in mind is the following. So imagine you have a family of Lipschitz domains, omega epsilon Rn, that are converging in a suitable sense that I will make rigorous in a while to a limiting domain omega. And we want to study the convergence of these eigenvalue lambda of omega epsilon, which are associated with either the Neumann Laplace operator or the biharmonic operator with some boundary conditions. And an interesting question is, first of all, whether these eigenvalues are continuous with respect to epsilon. And in many situations, this is not the case, and I'm particularly interested in the cases when this actually does not happen. So I'm a bit interested in these pathological perturbations where something sort of wrong happens. And somehow I will talk about stability of the eigenvalues, not in the nonlinear sense, but I will talk about it in a more specific sense that I will make rigorous in a moment. So whenever I talk about spectral convergence, I'm thinking about the compact convergence of the resolvent operators. And I will denote this with this arrow with a curly C on top of it. And it is well known that for self-adjoint operators with compact resolvent, the compact convergence of resolvent operators implies the convergence of eigenvalues and eigenprojections. And this is well known, goes back to the works by Nico and Tumble. And then, Weidmann somehow linked the discrete convergence to the norm convergence of the resolvent operators. And Sabine Bergli, in a recent paper, shows several relations between these different types of convergence, and she has several generalizations to the case of non-self-adjoint operators and more complicated cases. But anyway, so since all the operators I will talk about are self-adjoint and with compact resolvent, basically compact convergence is enough. And I was talking about spectral stability. For me, spectral stability means that apart from the continuity of the spectrum, I have also the continuity of the boundary conditions. And what I mean is, imagine you have the same operator on a sequence of domains omega epsilon that are converging to a limiting domain omega. Imagine you have the same boundary condition for every epsilon. You would like to know whether this boundary condition is preserved in the limit. I would say there is spectral stability if that's the case. So there are some typical examples you may look at in order to find pathological behaviors. One of the first perturbation that can come to your mind is the Dumbbell domain. But you could consider thin domains. So this is a sort of thin rectangles. This has size epsilon, and the limit will shrink to just a segment, or like this dark gray region that will shrink to the boundary of omega. Or you may consider other types of, let's say, pathological domains that have sort of oscillating boundaries. So they are locally defined as the subgraph of a very oscillating functions that will tend to this flat line as epsilon tends to 0. And depending on which operator you are considering on these domains, you have different spectral behavior in the limit. So let's see, for example, what happens in the case of the Neumann Laplace operator. So first of all, whenever you talk about Neumann Laplacian, you have to be slightly careful about the regularity of the boundary. Otherwise, the Neumann Laplacian may have essential spectrum. So here I will always assume that we have Lipschitz boundaries. And even though I'm not assuming a priori that we have a uniform Lipschitz condition for every epsilon. So in principle, this Lipschitz constant may be different for every epsilon. And so for the Neumann Laplace operator, there are at least two interesting spectral stability results I would like to talk about. The first one is due to Arrieta and Carvalho in JDE 2004, and somehow relates the spectral stability of the Neumann Laplacian to the absence of concentration phenomena, in the sense that the eigenfunctions of the problem will have no concentration of their L2 energy at the boundary. What I mean with this is the following. So think about a Dumbbell domain of this form. So you have this blue part that is the domain omega, then you attach a thin handle R epsilon, size epsilon. And now you can prove that some of the eigenfunction of the Neumann Laplacian will actually have L2 mass concentrating on this red part. And therefore, this criterion here is violated, okay? Indeed, on Dumbbell domains, you won't have spectral stability in general. And let's say another type of, another criterion for the spectral stability is given instead for interior perturbations. So if, for example, you are considering domain omega epsilon that are all included in omega, they are increasing uniformly Lipschitz, and the measure of omega minus omega epsilon is tending to 0 in the limit. Then there is a nice result by Davis and Burenkov in JDE 2002, saying that then the eigenvalues of the Neumann Laplacian are in fact continuous, and the boundary condition is preserved in the limit. Unfortunately, both 1 and 2, as I was saying, they are violated for Dumbbell domains and thin domains. And when you have a closer look to what happens, so there are, let's say, two types of Dumbbell domains. So the first one is what I call a regular Dumbbell. That is basically the union of a smooth domain omega that has a very nice boundary and has two connected components, let's say, that are connected with a thin channel R epsilon that has size as measured, that is, let's say, of order epsilon, then what happens is that the eigenvalues will converge to the union of two families of eigenvalues in the limit. One is what you expect, so they are just the eigenvalues of the Neumann Laplace operator in omega, but then you also have some additional eigenvalues that are coming from the thin channel R epsilon. And they will be the eigenvalues of a precise operator that can be characterized. And this was done, for example, in Jimbo 89, where he considered a straight channel. And then Arrieta and Arrieta Carvalho and Lozada Cruz, they considered the problem in a more general setting, and they were able to prove again that you have this sort of behavior. You could also consider, instead of a regular dumbbell, a degenerate dumbbell. So what I mean with this is that this part here will have a measure that will go to zero. So somehow all this little part here, this sort of mushroom, will shrink to a single point at the boundary. And it is well known, and this goes back to Coran and Hilbert, that the second eigenvalue of this problem tends to zero, provided the channel is small enough compared to the size of this little room R epsilon. And the other eigenvalues, instead, starting from the third one and going on, they will converge to, let's say, the right limiting point. This was proved, for example, in Arrieta, Hale, and Hahn in a wide generality, I would say. Of course, it is quite easy to generalize this example to, let's say, domains where you attach M thin handles, or better, M thin mushrooms. And then what happens is that actually the first M, sorry, this is a mistake. Well, okay, the first eigenvalue is always zero here. So what is interesting is that from the second eigenvalue to the nth eigenvalue, they will all go to zero. So enough for the Neumann Laplacian. Now I would like to switch to the biharmonic. And in order to do that, I need to talk a little bit about boundary conditions, because the boundary conditions for the biharmonic operator are a bit more diverse than the ones for the Laplacian. So if we start from the sesquilinear form for the Laplace operator, I know that in general, you could have other, let's say, boundary terms in here, and then the eigenvalue problem will be, for example, of Robin type. But here I want to keep things simple for the moment, so I will only consider this eigenvalue problem here, where phi is in V of omega. And depending on what the energy space is, you could have Dirichlet boundary condition or Neumann boundary conditions. Now, if we do the same, say, argument for the Laplacian, so we look now at this eigenvalue problem, where now this D squared means the Hessian matrix, and this column here is basically the Frobenius product of the two matrices. Then you actually have three main choice for the energy space. So of course you have Dirichlet that will correspond to H20. You got Neumann corresponds to H2, but then you also have intermediate boundary conditions that arise when you intersect H2 with H10. And intermediate boundary conditions are known to be very interesting from the point of view of spectral stability. We will see this in a moment. Let me see that the study of the Neumann problem for the B Laplacian is actually, I would say, rather recent. And for example, the solvability of this problem in Lipschitz domains have improved only in 2005 by Grigori Verkota. And then there are several nice results by Laura Chasman and collaborators about the optimization of eigenvalues of the free plate. That is, let's say, the physical equivalent of this problem. And Colbois and Provenzano in 2019, in a paper that I think is on arXiv, I'm not sure if it has been published now, they actually consider this problem on domains on manifolds. So before this paper, I'm not sure this problem was ever considered on manifolds. So this is telling you that somehow this is a rather recent field of investigation. And let me also say that very recently, Wozo and Kennedy actually consider Robin boundary conditions for the B Laplacian. So going back to the difference between the Laplacian and B Laplacian, there is this sort of difference in the fact that these intermediate boundary conditions are somehow very peculiar for the biharmonic. And there is something more behind this. So let me try to explain this. So when you consider the problem of extending functions and preserving at the same time the energy space, then you may run into trouble when you try to do it for the intermediate boundary conditions, because if you have Dirichlet, you can just extend by 0. And of course, the boundary conditions will be preserved because we know that when you extend by 0, somehow the traces will extend in a nice way, let's say. So a function in H2 will be extended to a function that is still in H2 of a possibly bigger domain, just because it is 0 outside the original domain. Now, if you take instead a function that is, for example, in H2, you can always extend it via a Sobolev type extensor. So you can do a easy reflection type argument on the boundary. You have to be slightly careful because here we are in H2, so you have to do a higher order type of reflection. But this is all well known and you can preserve the regularity. But what about intermediate? So if you try to extend by 0, then you will lose the H2 regularity. On the other hand, if you use a standard Sobolev type extensor, then you will lose the vanishing of the traces at the boundary. And a combination of the two will not work either. So you really need to be careful here. And as far as I know, there is not a canonical extensor that preserves this space. So this is a first stark difference, I would say, between biharmonic and Laplacian. Another one that I would like to point out is the behavior on thin rectangles. So if you have a rectangle R epsilon that is given as the product of gamma and 0 epsilon, gamma here is just, you can imagine it's a curve, like one-dimensional curve. Then, well, it is rather well known, and this is a result that, for example, is proved in Schatzman 96, that the resolvent of the Neumann Laplacian on R epsilon will converge compactly to the resolvent of the Laplace-Beltrami operator on gamma. This implies that, in particular, all the eigenvalues will converge. And the proof is basically It's just a matter, roughly speaking, of neglecting the dependence of the thin variable. So what I mean is, since you are very thin along this normal direction, your ansatz is that along these thin directions, the derivatives will have to vanish. So the derivatives of, for example, the eigenfunction in the limit will have to vanish because you expect the limit to be tangential, to lie on this curve gamma. Of course, in the case of the Laplace operator, we know that this type of heuristic argument actually works. And when you look instead at the biharmonic operator, this is much more complicated. And definitely, you cannot forget about these thin directions, because otherwise you cannot prove any sort of convergence. And this is somehow related to the fact that the biharmonic operator, I mean, for the biharmonic operator, you don't have a nice separation of variables argument, since it is well known that this fourth order operator is mixing the different derivatives. Now, all right, so let me proceed with another example that goes back to the 1960s, more or less. And this is really something very specific for the biharmonic operator with intermediate boundary conditions. So this is called Babushka paradox. You take a unit circle in R2, and you take a sequence of convex polygons that are inscribed, so they are inside the unit circle, that are convergent to omega, let's say in a pointwise fashion, and they have an increasing number of edges. Now you look at the intermediate boundary conditions for the biharmonic operator. So the two boundary conditions read like this. You have u equal to 0 at the boundary and second normal derivative equal to 0 at the boundary. And this is also called hinged plate problem and was studied by Babushka in 61. And the interesting point is that this sequence of problems have a rather interesting spectral behavior in the limit. So you would expect that somehow these boundary conditions would be preserved in the limit. But in fact, what happens is that these solutions un do not converge to the solution u of the same problem in the unit circle, but instead it switches in the limit. So the boundary condition is becomes this full Laplacian equal to 0 at the boundary. And somehow this is really the typical example of a situation where you don't have spectral stability, as I have defined it, but you do have spectral continuity, because if you take as limiting problem this one, then of course the eigenvalues will converge to the right place, and also the eigenfunction will. But somehow I'm more interested in this sort of spectral instability. So this really change in the boundary condition in the limit. And I would like to now consider a more general Babushka paradox, okay? And this is based on some work that I've been doing with Pierdomenico Lamberti in the last, let's say, 4 years, basically. So we now go and consider the intermediate biharmonic operator on domains that have oscillating boundaries. So the setting here is a bit more general than the Babushka paradox that we have seen before. So I'm assuming that the family omega epsilon and the limiting domain omega belong to the same C2 Atlas class. What I mean is that I can somehow cover the whole families of domains with a set of charts. And locally inside this chart B, so I could represent the boundary of omega and the boundary of omega epsilon as the graph of a C2 function, so that I will call G epsilon for omega epsilon and G for omega. And up to a partition of unity argument, if we are only interested in the behavior at the boundary, we could always assume that omega is equal to omega intersected V, and omega epsilon is omega epsilon intersected V. And now the question is, can we somehow give a geometric condition that implies the spectral stability of the biharmonic operator with intermediate boundary conditions? And so we would like this geometric condition to be expressed in terms of the convergence of G epsilon to G. So how to do this? Well, one has to work a little bit. It's not that easy, but let's say there is the following result. So I will call H of omega epsilon the self-adjoint operator associated with this sesquilinear form with this energy space. So this is again the biharmonic operator with intermediate boundary condition plus the identity. And now Arrieta and Lamberti proved in JDE 2017 that now if you have, again, the same energy space in the limit, so we are considering really the sequence of biharmonic operator with intermediate boundary conditions on this family that belong to the same Atlas class. And these two geometric conditions are satisfied, then you actually have the spectral stability. So the resolvent operator associated with the problem in omega epsilon will converge to the resolvent operator of the problem in omega. And the boundary condition is preserved because these two both satisfies intermediate boundary conditions. And the exponent 3s that you see here at the denominator is actually sharp. So let me comment a little bit on these two conditions. So the first one is basically telling you that G epsilon is converging to G in uniform norm. And the second one is now telling you that somehow you also have some convergence of the derivatives of G epsilon to the derivatives of G in L infinity norm. But this convergence is weighted with respect to the convergence of the functions themselves. And the interesting point is that when the length of this multi-index is equal to 2, so you are taking second derivatives, then you see that this guy here goes at the numerator. So the second derivatives are allowed to diverge in the limit. So somehow the convergence of G epsilon to G is weaker than the C2 convergence. And somehow this is quite interesting because it is, I would say, rather easy to prove that if you have C2 convergence of G epsilon to G, then you have spectral stability. But that is not sharp. Here, if you want a sharp result, you have to go below C2 somehow. And so I will now discuss a little bit this sharpness. I should say that these results I'm presenting now are based mainly on this paper by Arrieta and Lamberti that was then further generalized in a paper by myself and Lamberti in 2019 and another paper in 22. But I won't talk about that because it's going to be too technical and I will probably need another hour just to explain the several technicalities. Let me just say that this sort of result holds also for different operators and for different types of boundary conditions. But okay, let's stick to the harmonic operator with intermediate boundary conditions. And let me show why this exponent 3s is actually sharp. So the idea is we will construct a perturbation of basically a very simple domain that is just a product of one-dimensional intervals in our N. And we will perturb the upper edge of this sort of cuboid with a oscillating function, B. And you can see that this function g epsilon, when epsilon tends to 0, will vanish because alpha is greater than 0. So the boundary of omega epsilon is actually approaching the boundary of omega in the limit, but it is converging in a very oscillating function, in a very oscillating way, sorry. So somehow this type of convergence is a bit complicated, okay? And what you can prove, okay, so let me first show a little graph. So when alpha is equal to 1 here, you can actually see that the way these graphs are converging to this line is rather wavy. So this wavy pattern can be spotted at all scales of epsilon. Whereas if alpha is equal to 2, this graph flattens out very fast. And somehow, if you are at this level, you don't see this wavy pattern anymore. You cannot really tell. And this is somehow the idea behind the proof. So somehow, if alpha is big enough, you will flatten out very fast, and then you will have spectral stability. If instead you are like below a certain threshold, then you will have this sort of wavy pattern. And if the oscillation is quite fast, then somehow you cannot tell the difference between a normal direction and a tangential direction. So this is telling you that probably the boundary condition in the limit will change. And indeed, that is what happens. So Arietta and Lambert in 2017 proved that if alpha is greater than 3/2, then the biharmonic operator with intermediate boundary condition will preserve the boundary condition in the limit. So there is spectral stability. If you are below 3/2, then instead you will converge to the biharmonic operator with Dirichlet boundary condition on the upper edge. And now if alpha is exactly equal to 3/2, you have a very interesting case where the limiting operator has sort of strange boundary condition that is a sort of interpolation between the intermediate boundary conditions and the Dirichlet. It is expressed in this form, where this red K here is called strange curvature, and this somehow can be characterized as the energy of a biharmonic function somehow related to B, that was the function defining the oscillation. So in particular, this is telling you that the hinge plate on omega epsilon is spectrally stable if and only if alpha is strictly greater than 3/2. And this is somehow complementing a known result from Mazia and Nazarov in '87, where they proved that in the case of the Babushka paradox, so if you consider instead of regular polygons, indented polygons, then they also have a sort of ratio between some measures of this indentation, and that ratio happens to be 2/3, so really the reciprocal of this number. And indeed, these two results are deeply related. But enough for this talk, because in this last, let's say, 20 minutes, I would like instead to focus on the Neumann biharmonic operator. So before moving on, can I ask if everything is clear, if there are questions on this particular result? Doesn't seem the case, so I will move on to the Neumann biharmonic. And I will first consider the case of Dumbbell domains. So I'm pretty sure that many of you have considered during their career at some point the Dumbbell problem. So a Dumbbell domain in R2, as I was saying before, is basically the union of a smooth domain omega having two connected components, omega left and omega right. And I will connect them, I will glue the two components with a thin channel that is given in a precise way. So it's basically the subgraph of a function g times epsilon, okay? So a picture of it is more or less like this. So the channel is really connecting these two parts. And all right, so here I'm assuming that the function g is a class C2 and is strictly positive. You could, of course, assume that the derivatives here are such that this is a very smooth junction somehow between the channel and the domain omega. That would be also admissible. Now, on this Dumbbell domain, we consider the Neumann problem for the biharmonic operator. And I will consider a slight generalization of it, where there is an additional parameter that is called Poisson coefficient of the plate. And this guy takes value in between -1 and 1. And okay, the function u, that is the solution to this problem, will be in H2. And the weak formulation is actually rather nice. So it's just a convex combination of the products of the Hessian matrices and the products of the Laplace operators. And now the question is, okay, so what happens to these eigenvalues in the limit? We have seen that for the Neumann Laplacian, you have this sort of two families of eigenvalues in the limit, and you expect the Neumann harmonic operator to have a similar behavior. Actually, that is true, provided you are sort of careful on the geometry of the channel that is connecting the two parts of omega. And you have to somehow assume that you have an additional geometric condition that is usually called H condition in the literature. And basically, roughly speaking, what it's saying is that in a neighborhood of this junction L epsilon between R epsilon, that is the thin channel, and omega, that will be on both sides of this picture, you want this red part to be regular enough. And what I mean with this is a bit complicated, like there is a functional condition that tells you when you can consider these red parts to be regular. But let me say that for a lot of channels, of reasonable channels, this condition is satisfied. So for example, if you have some sort of monotonicity property of G, so if G is monotonically decreasing in a neighborhood of 0 and is monotonically increasing in a neighborhood of 1, then this H condition is satisfied. It's rather technical, so I won't go too much into details, but it is important that you have this sort of additional condition. Otherwise, there are counterexamples somehow where to the theorem I'm going to show to you in a moment. So just to fix the notation, in the channel, I will call L epsilon these two junctions, and gamma epsilon these two long edges. Now, we are looking at the eigenvalues of the biharmonic operator in the Dumbbell. And what you can prove is that there is a sort of asymptotic spectral decomposition. So in the limit, the eigenvalues will be close to those of either one of these two problems, either to the eigenvalues of the biharmonic operator in omega, or to the eigenvalues of a mixed problem with Neumann and Dirichlet boundary conditions in the channel R epsilon. And okay, so if you define lambda and epsilon to be the union of the eigenvalues of these two guys, and you write them in increasing order according to multiplicity, and you moreover assume that you have this H condition, then you can prove that asymptotically the eigenvalues of your original operator are close to these eigenvalues here. I should say that the ordering of these eigenvalues is somehow epsilon dependent. So you got to be slightly careful. So when you say lambda n, so this nth position could change when epsilon changes, okay? Because maybe some of the eigenvalues will that are very small will come from the channel, and the larger ones will be from omega. So they could somehow change position. So you really have to write in this way. And once you have this result, you can actually study what happens in the thin channel as well. And again, it's a bit technical, but what you can prove is that in the limit, the eigenvalue will converge to the eigenvalues of a ODE in the segment 0, 1 with Dirichlet boundary conditions at the extremal points. But the interesting point is that this quite interesting factor 1 minus sigma squared appears in front of the principal operator here. And this is interesting because of the following. So if you prove, when you prove this, you actually prove that the second derivatives in y, so in the vertical direction that is supposed to be thin, is actually converging weakly to a tangential second derivative. So have a clear non-trivial contribution of the thin directions. Of course, as you can see, this could depend on sigma, right? So if sigma is 0, somehow you don't see this. So you could say, well, look, of course, you are considering a very complicated example in which you have this parameter, and maybe, you know, if sigma is 0, then you don't see this difference. That's true. But I would like you to keep in mind this sort of non-trivial contribution of the thin directions, because now I will show to you that actually this is something that is deeply related with the specific form of Neumann biharmonic operator. I will do this in this last part of the talk. So I'd like to now focus on a recent work that I've been working on with Luigi Provenzano from Sapienza University of Rome. And this goes back to, I think we started to consider this problem in 2019. So it took us quite a long time in order to find a final result. I remember I was in Padua in 2019, and Luigi came up with this problem. So basically, think about a smooth bounded domain in R2, and you consider a tubular neighborhood of the boundary ring. And now you consider the Neumann eigenvalue problem for the Neumann biharmonic operator in omega h, and you want to know what happens to these eigenvalues mu h when h tends to 0. So again, this sounds like the same thin domain analysis that I was doing for the Dumbbell. So Luigi knew about that result, and he asked me, okay, can you actually prove what the limit of this eigenvalue is? And I was quite optimistic. I thought, okay, I know how to do this, right? I would just forget about somehow the thin direction, and we'll take the limit, and the limit should be just the fourth order operator along the tangential components of the boundary. So I would just forget about the normal components. But actually, then we started to do some computations, and we realized that it was not really what was happening. And indeed, for the biharmonic operator, you don't have the analogous of the Schatzmar result. And this is can be seen quite easily using a quite recent result by Colbois and Provenzano, where they proved that the spectrum of the biharmonic operator on the boundary is the square of the spectrum of the Laplace-Beltrami operator. So basically, what happens is that the first eigenvalues has multiplicity 2, and it is equal to 0. The second eigenvalue, again, has multiplicity 2, and it is strictly bigger than 0. However, in our situation, we have that the first 3 eigenvalues are always 0, because somehow our operator has a 3-dimensional kernel. This can be easily seen since the polynomials of degree at most 1 are in that kernel. And so in particular, it cannot be that the limiting operator is this biharmonic operator at the boundary, because the multiplicity is changing, right? And we suspect that the multiplicity should instead be preserved. So we started to do some explicit computation in the unit ball, and using spherical harmonics, I remember that Luigi at some point has shown this to me, and he said, are we sure that this is correct? It looks like, there's something strange in here, because L is somehow the index of the spherical harmonics. And you don't expect this L to be at the denominator, right? Usually it doesn't appear there. So it's rational now. And we were thinking, okay, there must be something wrong. And we were thinking and thinking. And then at some points, we realized that the problem is we were expecting the limiting operator to be just a differential operator. But instead, it's like a pseudo-differential operator. So it can be expressed as a system of ODEs instead of a single equation. And well, let me show first a nice picture of the convergence to these limit points. So these are the analytic branches of mu H. So here you have H, and here you have this parameter L, and the dashed lines are just these numbers appearing here. And you can see quite clearly that you have convergence to those dashed lines. So this result, at least numerically, is definitely correct. The problem is how to prove it. And well, it took us almost 3 years, but now we have a precise statement. So the limit eigenvalues are the eigenvalues of this system of ODEs, where the eigenvalues appears only in the first one. So the second one is, I would say, a bit of a dummy equation, in the sense that you could express W in terms of U by inverting this operator. You can do it, but then you would have inside here some sort of inverse of the Laplace operator. So if you look at this full thing here, won't be differential anymore because you have inverted the Laplace, and so this would be a sort of pseudo differential operator. Of course, we can deal with that. It's just that you're always expecting somehow a nice form of the limiting problem, since you are starting from something that is actually very nice. But instead, in this case, the limiting operator has this quite involved form. So I should say that here kappa is the curvature of the boundary of the omega. So you can see that somehow if kappa is 0, you don't see anything here. So a lot of terms will just be 0. And actually, I should say that the case when kappa is exactly equal to 0 is not covered by this result. We really need that kappa is not 0, at least on a small subset of the boundary. And okay, we also have, apart from convergence of eigenvalues, we have convergence of the eigenprojections in a suitable sense. So I guess I have probably a couple of minutes, I hope so. So I would like to just show briefly a sketch of the proof of this theorem. So the idea is actually very simple, and it is something that is very natural. So you first start from this domain omega h, that is the tubular neighborhood of the boundary, and you just apply a diffeomorphism that is, let's say, the standard one that you use when you look at the tubular neighborhood. So as here plays the role of the arc length, and what happens is that this diffeomorphism is basically mapping this rectangle sigma onto omega h. So you're basically straighten out the boundary, and you're now looking after this change of coordinates to just a rectangle. And all right, so these are usually called Fermi coordinates and well studied. But now the problem is you have to do a pullback of the form. So this is a bit painful, but you can do it. And the important thing is to use Bochner's formula. I mean, you can probably do it even without using this formula, but everything is much more complicated if you don't use that. And the chance you get it wrong is very high. So you actually compute every term on the right, and in this way you recover the product of the Herschel matrices. And finally, you prove compact convergence by basically proving the convergence of some rescaled problems in sigma. And okay, so this looks a bit complicated, and indeed, I have to say it's quite technical. Let me just mention that the 3 ingredients you need here is first a coercivity estimate that you need in order to pass to the limit. And here the curvature is somehow really playing the role of an additional hurdle in the analysis. So you always have to take care of it. And in many cases, it's really painful somehow to have to deal with this curvature because it can vanish on a non-trivial set. And then, you know, you don't have a clear lower bound sometimes. So you really have to be smart here. Okay, you can do it. And once you have that, you can choose the test function in a suitable way in order to pass to the limit. And finally, you need a weak to strong convergence argument in order to recover compactness. So this is rather standard. And all right, so I'm running out of time. So let me just switch to the end. And so this is a set of references for many of these problems I'll be talking about. So thank you very much for your attention.
Thank you very much, Francesco, for this very nice talk. We have time for questions now. So please, as usual, relay your question in the chat or unmute yourself and go ahead.
I have a question. So in the last year and a half, I guess, whenever I've heard talk from people talking about biharmonic operators, they had a very large family of these intermediate boundary condition coming with parameters and with many names that I never can remember. Is your case of this intermediate boundary condition encompassing all of them, or it's one specific case?
So yeah, it depends, right? So let me go back a little bit. So I guess you were referring to these results here, right? For example, these this quadratic form here. So I should say this is not the most general one, because the most general one would involve the so-called Poisson coefficient, that is the same sigma that we have seen later on for the Neumann biharmonic. If you are interested in this kind of stuff, I would actually refer to this paper by Wazo and Kennedy, where they define these Robin boundary conditions, and they have probably, I would say, the most general setting that you can have for the several possible boundary conditions. I should also say that I tried to keep the talk quite easy, so I've not considered the most general case. But yeah, in principle, there is a set of boundary conditions depending on this parameter sigma. So you are completely right about that.
Yeah, I mean, I didn't know. I didn't know if it was, if your result was more specific or not, but thanks. That really answers well the question.
Thank you. There is a hand raised by Massimo. Please go ahead, Massimo.
Yes, can I ask my question? So I've seen that you have some continuity results for the eigenvalues, and my question is that with these methods, is there a way to give an estimate between lambda epsilon and the limit? Some sort of a first order asymptotic, or?
Yes, this is thank you very much for this question. So I should say I'm not sure that for all these cases that we have been looking at, you can actually provide easily a first order asymptotics, but I'm pretty sure that in many of the cases you can. And the idea is that usually you can somehow lift up the compact convergence of the resolvent operators to the norm convergence of those operators. And if you can do that, you can usually provide a sort of error estimate, and you can provide a corrector term that will give you a sort of quantitative estimate of these eigenvalues. So I've seen some papers doing this, in particular by Olaf Post recently, and I believe that his methods probably can be applied, also to these situations. But I'm not sure how difficult it is. It can be very complicated.
Thank you very much.
Thank you. Anyone else would like to ask something or comment? If not, I think we should thank our speaker again. Thank you very much.
Thank you.
And we will return next week with a talk by Maxime Fortier-Bourque, who will speak about the multiplicity of lambda 1 for surfaces of genus 3. Have a safe week and see you next week.